Good morning to Advent of Code 2020, day 8. Treetop Treehouse. The expedition comes across a peculiar patch of tall trees, all planted carefully in a grid. The elves explain that the previous expedition planted these trees as a reforestation project. Now they are curious if this would be a good location for a treehouse. First, determine whether there is enough tree cover here to keep a tree house hidden. To do this, you need to count the number of trees that are visible from outside the grid when looking directly along a row or column. The elves have already launched a quadcopter to generate a map with the height of each tree, your puzzle input. Each tree is represented as a single digit whose value is its height, where 0 is the shortest and 9 is the tallest. A tree is visible if all other trees between it and an edge of the grid are shorter than it. Only consider trees in the same row or column. That is, only look up, down, left, and or right from any given tree. All of these trees around the edge of the grid are visible. Since they are already on the edge, there are no trees to block their view. In this example, that only leaves the interior 9 trees to consider. Top left, 5 is visible from the left and top. It isn't visible from the right or the bottom since other trees height 5 are in the way. So a tree is visible if all other trees between it and the edge of the grid are shorter. So it's exclusively. The top middle 5 is visible from top and right, and so on and so on, with 16 trees visible on the edge and another 5 visible in the interior. A total of 21 trees are visible in this arrangement. Consider your map. How many trees are visible from outside the grid? Okay. In this case, it's a total of 21. We'll copy that. This is our example input. We have 21 trees visible, and we get our puzzle here. Fairly big one. Let's hop here. So, let's just think this through, how we want to iterate this. We would actually like to iterate rows and columns. Do we want to save the adjacent ones? Not really sure about that. Yeah, so what I would do do checks from all four directions, and we'll keep an array of trees, and we'll keep an array of we already have this kind of array for trees. That's fine. These lines can do that, and we'll just keep but we don't know how big to make this one. Yeah, and we'll keep a Boolean grid where we just check which tree is still visible, and we tick those boxes there, and that's it. So I would start with the sweep from checking from left to right, and therefore would say lines, and we then need to check the individual line, and the individual line in line and then we have here var max line, which is initialized with c0 with line 0, and if the max line is if max line drop 1, and then we have our get to the dimensional array here. This is visible. And we make it an array of string. Is this how to do it? I think it's array. Is there something like an array of in Kotlin? Let me just check. To the array in Kotlin. And is this really a string array? This actually feels all a bit weird, but well. Would prefer this where row. Think okay, so like this, and we do an array in then this with the height, which is lines.size, and then we want to have the elements in there, and this is array of type string, and we'll supply line 0 dot length lines 0 dot length lengths yeah, that's okay, but first dot length. So what? Why does it? No value passed for parameter init. Just want to have an array of int. Not of int, but of string. Which seems to be fairly complex in Kotlin. Then let's just do it like that. List string I've actually never worked with two-dimensional data structures in Kotlin. This turns out to be weird. Or at least, yeah. Well, we'll need to have it mutable, but okay. Would actually like to have it initialized as well. Okay. But then let's do that here. So the first line will say add mutable list. Put here the mutable list. Add mutable list, and then we can have our list here. Add the mutable list exactly, and then we would also say visible Can we automatically get an index in Kotlin? For each indexed. That's what I wanted. Dot with index. So we have our index. We have our line. And add position index. Dot add. In this case, the var, we call it sweep. We take letters to indicate from which position we've reached a tree or not, so we can easier debug an error afterwards. That means let's add visible dot add initialize it before for I in range 0 until visible dot length size. Then for j in 0 until lines at position 0 dot length, and then we can say visible at position I at visible add mutable list of, and we have visible at position I. Of string, and then we say current line dot add an empty string, and then we add this current line to the visible line, and then this should be set. Yeah. So then we have our sweep from the left. We start with the 0 value, the 0 value, we start with the first index, is always visible. We know that. That's why we already go here and say visible at position 0. I think we can at position index and at position 0. We say plus equal to our sweep. And for all the others, we check if the max line is smaller than the self. And if this is the case, we also add them to our sweep. And we set max line to be the C. And in the else case, we do actually nothing. The only thing we can do is we could actually else if max line is equal 9, is equal to we are still working with the character here, 9, then we can do a break, because then there can't be any higher higher values anymore for this sweep. And this is now from the sweep from left to right, which is convenient because if we can do it with the index like this, but we should also be able to do it the other way. So yeah, we should swap this, or we can do them reversed. Can we reverse this? This can be reversed. This is nice. And we can also reverse the line actually. Yeah, I would just now try to do that. So we have the left sweep here. And the visibles are set. Then I will do the right sweep here. And for the right sweep, we want to have the line here actually reversed. So we say, can we do this? Line dot reversed. And we can't assign it like this. So we'll say just R line, and we use the R line instead of the line here and here. And we update our sweep to an R. That's the only thing we changed. And what we now want to change, we now also want to change it top to bottom. So this is going down from the top. We now want to do it from left, right, yeah, starting with you. So we say that we start with a line here. But here we now actually need to start max line. Line is 0. We'll need to iterate in a different way, which is kind of annoying if we iterate over the line here. Can we? We can access them two-dimensionally, right? So I think that's maybe even easier. Yes, I think we should be able to do that. So we'll create our index loop. Basically, we can reuse this stuff here. For an index loop, we can actually use the visible here. Then we can use the first, and this should be size then. Yeah, let's just use those loops. This will make it a bit easier to just switch out the directions and the indices we access. So in this case, we also have the max for our scan lines at position 0 at position 0. We here will start with 1. Yes, because we also need the indices for this one, yeah. But we also need to start with the reverse thing here. Yeah. The max line here. So I'm actually not feeling that confident here. We have our lines in this order. So how can we can't just reverse this, because then we can't access the visible as we should. And if we just sweep over it, we can just sweep over it in the different direction. Let's do the left one first in this style, and we should then be able to do the sweep in the different direction, and yeah. Okay, let's do the left one in the index way first. We start all over the lines, and we have the max line here. We have the j set to 1 until we go there, and we can basically do this. So if our lines at position, or we can extract this character here, c is equal lines, and we'll now want to have the position I, and we also want the position I here, and we want the position j here, and we want to access it at I j, and we add it for the sweep. And we can now also do this for the right sweep. To R. And for the right sweep, we just want to iterate over those indices in the different direction, but not of the lines, but of the of each column. So we'll start out with visible at position 0 dot size -1 down to 1. So let me check, it's greater or equal this, that is fine. Down to greater equal 1, this is also what we want. And no, down to 0 in this case, greater or equal smaller or equal this one, yeah, that's fine. And here then we want to have the last element, which is visible dot size -1. The last element will be visible as 1. And I think here we should actually have the I in there, although it shouldn't matter. -1. And we're now doing the same thing. So let's get rid of this. And now let's try this for the sweep from above. For the sweep from above, we now need to change the index axis. So we will, let's start with the one from above. Let's start with this one as a base. That means we now want to access element the element 0 at the indices 1, but we'll therefore need to have the right loop in place here. The first line and the ith element. For this thing here, we then want the size of that here, and we'll scan with j and I, and we set with j and I. Okay. And sweep. How did they call it? Called it up, down, left, right, down. And we can also use the D here. So then we want this to be changed. We now want to have the lines to start with the lowest line. So we want to start here with visible dot size -1, and we want to loop from no, this variable should still be, no, we swapped the indices, so it should be the 0. Yes. That's when we take the 0 here. And we want to go down from this one down to 0. And this is greater or equal, so we have the -1 here. We actually want to have the -2 here. And started 1 here, right? So we want to have this one to the -2. Have the max line here set to this. And then for the other direction as well, I think we'll just take this. We just need this construction here. And we should have our lines where we access the j and the I. That's fine as well. Let me just check this. We want to start with size -2, right? And we'll run 2 including the 0. And what we'll now still need to do is we'll need to set the visibility for the 0 element, which we haven't done yet. So the visibility of our 0 element, which is this indices here, will definitely, so this will be definitely visible. So we'll do that for here as well. Plus equal sweep. And we'll put that away for now. So, and now we would like to know which elements are visible so that we can take our visible and we'll just sum off it dot sum off, and we'll just count where it is equal to is blank. On invisible, visible. This is a count. And then we have visible dot size times visible 0 dot size total, and we return total minus invisible, and we'll put this to string. So, and then let's run it. Cool. So this is more interesting. Let's see. So we have at least the size 5 by 5. And this is visible from the left. This is visible from the left and the right. Because it's the 7, that makes still sense. This is visible from the left, and from the left we have the 5, and from the right we only have the 2 visible, and we have the second 5 visible from the right. But yeah, this is a 1, that's fine. And for this one we have the left visible, we don't have the 3, we get the 5 again, we get the 9, and we only get the 9. And we get the 3, we get another thing, we don't get the third 3, we get the 9 obviously, and we also get the right, although it's a 0. Oh, okay. So now comes the thing where I expect to have fucked up. So let's have a look. Visible. So the first one, they are all visible, that's good. And we have only those 2 visibles, only the 5s, which makes total sense for now. Let's check it for the down. All those are visible. No, this one isn't, and this is wrong. No. Let me check. No, actually, all of those are visible from above, right? But why isn't it getting that one? Let me just check. Do we have the L here all the time? The up. We have it up all the time. We have it only here. Then we have the up only on those 2. Then we get an up for the 6, which makes sense. Which we also have in the down. Yeah, that also makes sense. Then we have the up only on the 4th for the 3rd line. For the 4th line, which is the 9. And then we have an up for, we'll get it for the 3, which also makes sense because it's also for the highest. Yeah, okay. But our down is not really working because we don't get the 4 here. Now let's have a look. The indices we would be accessing would be 4, 4, and 4 would be the I, and we'll say size -2, which for this thing here is not correct. It must be -1. So yeah, okay. Then let's run it again. Yeah, we are correct for this one, and this is ours. Let's give it a try. Part 2, content with the amount of tree cover available. The elves just need to know the best spot to build their treehouse. They would like to be able to see a lot of trees. To measure the viewing distance from a given tree, look up, down, left, and right from that area. Stop if you reach an edge or at the first tree that is the same height or taller than the tree under consideration. If a tree is right on the edge, at least one of its viewing distances will be 0. The elves don't care about distant trees taller than those found by the rules above. The proposed treehouse has large eaves to keep it dry. So they wouldn't be able to see higher than the tree house anyway. In the example above, consider the middle 5 in the second row. Looking up its view, it's not blocked. It can see one tree of height 3. Looking left, its view is blocked immediately. It can see only one tree of height 5 right next to it. Looking right, its view is not blocked. It can see 2 trees. Looking down, its view is blocked eventually. It can see 2 trees, one of height 3. Then the tree of height 5 that blocks its view. A tree's scenic score is found by multiplying together its viewing distance in each of the 4 directions. For this tree, this is 4, found by multiplying 1 times 1 times 2 times 2. Scenic is found multiplying together its viewing distances in each of the 4 directions. However, you can do even better. Consider the tree of height 5 in the middle of the 4th row. Looking up, its view is blocked at 2 trees by another tree with height of 5. Looking left, its view is not blocked. It can see 2 trees. Looking right, its view is blocked at 2 trees by a massive tree of height 9. So let's check again. Viewing distance for a given tree. Look up, down, left and right from that tree. Stop if you reach an edge or at the first tree that is the same height or taller than the tree under consideration. Okay. So So this is now our current, we can say var, this is a current tree score, and we want to, we need a best tree score, which we can initialize. I think with 0, then we need an var best index, which will initialize best line. What do we need? Do we need to know where it is? What is the highest scenic score possible for any tree? Don't really need that. And then we can here now we just need to move, and we will move for now in let's do the check to the left. Let's start with let's start with checking further to the left. So we call this view I. I should be in the range of our current I until we are at the end of the line. And if we just extract our current tree, which is lines at position I at position j, and should we convert I can't do that later on, right? Need to multiply those scores together and like all of them, right? So looking up, it's blocked from at 2 trees by another tree with height of 5. Yeah, we just need to count them in that direction. So yeah, the height then doesn't really matter. And then we check if our lines at position I plus vi, oh no, if we do it like that, we just allowed to access vi, and at position j, if then we have a var tree count 0, then we will say tree count tree score is 1. We'll have that as a base for multiplying later. And if this one is as long as this one is smaller than our tree, let me just check. Measure distance from a given tree, look up, down, left, and stop if you reach an edge or at the first tree that is the same height or taller. Okay, so if this is smaller than our current tree, then we can say tree count plus plus. Oh, let's do it. Yeah, and else we can also say tree count plus plus, but we'll also need to break the loop because we are not longer allowed to count the trees. But that actually means we have at least one tree in any direction except when we are on the edge, but then we get 0 iterations here. So that actually also means that in the edge, if we do this multiplication, we'll end up with 0. I think that kind of makes sense. Oh. And then we say the tree score is multiplied with the tree count. This is now for going left. Now also do right. We need to reset that. We don't do it for the tree count. Then we say for I, from I would be our starting point here. We don't want actually that. We want to have it +1. And from that direction, we want to have it -1 down to 0. So it must be greater equal 0 and is -1. This is fine. Then we do the absolute same. And yeah, we'll just copy that. No, we copied it. Do it. Then we'll reset our tree count again. And in this case, we call it yj, we call it j here. We now look down first. Down. The yj, in this case, that's actually a point in here. We need to check. We're actually not looking left first because the first index is the line index, so we're actually looking down first. But this is actually down. This is actually up. Yeah. But we are fine with having the lines here. In here we need to check this one. This one is now to the left, where we say we start with this. We want to have the yj here, and we want to stay until, so smaller equal, we don't access that, that's fine. And we want to have this again. This should be right. We get the tree score again. And for right, we'll say we start with -1 here. Down to 0. And now we can say if best tree score is larger than tree score, then we say best tree score is equal to tree score. So then we'll need to run the puzzle 2 here. We want to copy over our inputs. We modify the example. And in here, this is the end of this method. So we have here the return best tree score to string. Oh. So this is again, I'm really not good at this. Is 4, but is expected to be 8. Okay. Then let's just, we want to debug until condition, and we want to check the, let's say if we look at this tree, that means that our I is equal to 1 and our j is equal to 2. Done. So our current tree is 5, that's good. And tree score, tree count, that's 4. Yeah. So we now start counting, and it's blocked of 1 tree. That's, you can see 1 tree. Yeah. Let's see. Yes, we get the 1 tree. We get another loop. We're looking down first. Looking down, we can see 2 trees, one of height 3. Then the tree of height 5, that blocks its view. Yeah, okay. Then we have now the tree of 5, and we get a tree count of 2 for that one. That's good. Then for the other pass up, we get 1 tree. And for the pass left, we should get 2 trees. We get the 2 trees. And we'll now get to the right. And for the right, we should... for the right, we immediately have the 5, which will only give us 1 tree. So the tree score is 4. For this one, that's correct. And the best tree score is 1. Our tree score is 4, and we set this best tree score to our tree score. Then let's go here. And we want to check another one, which is I is equal to 4. And j is equal to 2. I is actually equal to 3. It's the... Yes. And then that... equal to 3, and j is equal to 2. So. Do we now have this situation, or don't we? Do we have just a regular breakpoint? I is 3, j is 2. Okay. Then we check for this one. We should have in the down direction is also not blocked. It can see 1 tree. Let's see. Yes, we have 1 tree. For the upward direction, we should get 1, 2, actually 2 trees. 1 we can, yes, that's fine. Then for the left, we should get 2 trees. This one, and that's it. So we are currently at a tree count of 2, and we are at tree score at 4. And for the right, we should now also get 2 trees. Let's see that. So the current tree is the 5. And the tree we are checking. Oh, this is a mistake. This is also wrong here, right? We're not allowed to have the J here. It must be an I here. And I wonder how we got the J here. Okay. But that's definitely not sure if it's the only problem, but it's at least that problem. Good. Now I have this solution, and let's give this a try. Okay. So I actually kind of expected that if we keep the sweeps with the direction here, that this is gonna be beneficial for the second example. Maybe if you would have built up a grid of trees and then had adjacencies set, and you could iterate through those, that would have been easier. Did not really see that coming, so that's why I didn't build it that way. But I think fair enough, we had a actually kind of Nice solution for the second one. Yeah, thanks for joining in. Have a nice day.